All right, so this is part 5, how blood flow is routed throughout the body based on exercise and rest. So one of the things you have to remember is that while you have typical resting cardiac output of 5 liters per minute, which is about the same as your total blood volume going through the heart every minute, at rest you're going to increase that cardiac output with exercise. You remember the concept of cardiac reserve, and we usually measure that by how many times you've increased over your resting value. So if your cardiac reserve is 7, then your maximum value is 7 times as much blood. That would be 7 times 5, 35 liters per minute going through your heart. Now, that doesn't mean that all of that blood is going to go equally to all parts of the body. Some organs will see an increase in flow, and some will see a decrease. And of course, this makes sense. If you're actively running, you're going to increase blood flow to the skeletal muscle of your limbs, and to the diaphragm because you're breathing, and to the heart because you're making it work harder. But you're going to decrease blood flow to, say, your guts, perhaps to your liver, and definitely to your kidneys. And we're going to see that there's a special regulation of blood flow to the brain. So we're going to constrict blood flow to the intestines with exercise and increase blood flow to the legs. That makes sense. At rest, you constrict blood flow to the legs, probably not as much as that diagram shows, and increase blood flow to the intestine when you are digesting a meal. All right, so at rest, the total cardiac output, 5 liters per minute. Look at the pie chart on the left. You don't need to memorize these values, but it helps to get some idea of relative amounts. So look at your cerebral circulation on the left in sort of a purple color, 700 milliliters per minute. Renal, right below that, about 1,100 milliliters per minute. 22% of your blood flow at rest goes to those 2 little fist-sized kidneys because they're filtering the blood. They need a lot of blood. Muscular, up there in the green, about 20%, about 1,000 milliliters per minute. I've seen different figures in different books, so don't worry about the exact values. Your cutaneous circulation in sort of an orange color, 300 mils per minute. And of course, that depends on whether you're cold or warm. Now, look at the one on the right. First of all, they should have made this pie chart bigger because it's what? About 3 times more blood flow. But look at how much is going to your muscles, about 12 times. So most of that increase in flow is going to your skeletal muscles. Of that 17.5, 12.5 is going just to your skeletal muscles. Digestive reduced, renal cut in half. Look at the cerebral though, still about the same, 700 to 750 milliliters per minute. Your brain needs the same amount of blood flow whether you're awake or asleep, whether you're dreaming or not, whether you're tired or alert. You change the flow within the brain to different parts of the brain, and that's the basis of PET scans and things that are looking at directional blood flow within the brain, but the brain as an organ always needs about the same amount of blood. Now, if you've increased your total cardiac output by 3 times, then you've got to actually constrict the cerebral arteries in order to reduce the amount of flow going to them. So with an increase in cardiac output, you actually see vasoconstriction within the cerebral circulation so that not 3 times worth as much blood goes to your brain. Those arteries up there are pretty delicate, and you don't want to burst them. And of course, look at the cutaneous. In the active state, it's going to get about double or more of the total circulation, depending on whether you're looking at percentage or actual amounts. So all of that should make sense. I think the only one that seems weird or odd is the cerebral circulation. Really doesn't change that much. All right, this diagram's a little bit better because it does show you how the blood flow increases. I took this from another book. And so you're seeing, look at the flow to the kidneys. It's decreasing by about half. Skin increasing by almost 4 times. Skeletal muscle by about 10 times. The heart by about 3 times, but the brain staying about the same. All right, so, and this is just a little histogram that I created myself, again, to compare that same difference so that you can see how much more blood is flowing when you have an increase in cardiac output. But that's basically the same values, so you can make that same comparison again. Okay, so just drawing the lines, you can see from the bottom to the top, increase in coronary circulation, increase in cutaneous, cerebral about the same, renal cut in half, digestive cut down considerably. All right, so we're going to work on capillary exchange. Now, this is probably the most complicated part of the overall chapter. This is where students tend to have more problems than anything else. And we're just going to kind of review capillary wall structure and types. Just remember you have continuous capillaries, fenestrated capillaries, and the sinusoidal. And as we look at capillary exchange, we tend to look at it in the continuous capillaries and then say, oh yeah, for fenestrated you're going to have increased flow. For sinusoidal you can have free mixing of the blood and the tissue fluid. You probably should review the processes of diffusion, osmosis, filtration, and transcytosis, but I will go through them as I go through this lecture. And then make sure you're aware of the direction of movement of nutrients. Nutrients from the capillaries to the tissue spaces, waste in the opposite direction. We're going to have some problems that you're going to solve. Those problems are actually posted for you in a PDF in the module, and you will definitely have some capillary exchange problems to solve on the test. All right, in this diagram, let's just make heads and tails out of all the arrows. So looking at the bottom, you have blood flowing in the arterial end of the capillary and out the venous end. This little red vessel here is a capillary. Imagine it as a continuous capillary with those intercellular cliffs letting fluid flow through the wall. So you actually have tissue fluid formed as plasma leaks out on the arterial end, and then on the opposite end you actually have fluid leaking back into the blood. And so we have a net movement out on the arterial end and a net movement back in on the venous end, but you still lose some of that excess fluid to the lymphatic capillaries. It says about 1/10 of the volume is going to leak into the lymphatic capillaries. So we've got to look at all these factors. We have two primary antagonistic pressures. We have blood pressure and osmotic pressure, which are working in opposite directions. Blood pressure is higher at the arterial end, lower at the venous end. Osmotic pressure, we tend to average across the length of the vessel. So the primary determinant in the flow of this fluid from plasma to tissue fluid and back is going to be that precipitous drop in blood pressure as blood flows from the arterial end of the capillary to the venous end. All right, so here are those pathways. We have in the fenestrated capillaries, we have those filtration pores that can let fluid leak out. Transcytosis is a vesicular process, endocytosis on the inside, exocytosis on the other side. This is mostly for getting proteins selectively out of the blood because proteins cannot go through those intercellular clefts that you see at the bottom. Diffusion through the endothelial cells is going to be limited to small lipid-soluble substances like oxygen and carbon dioxide. So let's focus on those intercellular clefts. Every component in plasma except the plasma proteins can leak out through the intercellular clefts without any barriers. So if you have, say, a concentration of glucose in the plasma of 90 milligrams per deciliter of blood, then as that fluid leaks out through those intercellular clefts, the concentration of glucose is unchanged. So it's going to be 90 in the plasma and 90 in the tissue fluid as it first forms. So in that way, nutrients can be pulled out just without being impeded through intercellular clefts, being pulled along by water. Just another diagram showing the same thing. So you have simple diffusion on the far left, oxygen typically leaving the blood, CO2 going in. Transcytosis can go in either direction. Proteins can leave the blood or enter the blood through transcytosis. Your intercellular cleft is shown in nice detail here. And then at the bottom, that sort of a gray-brown colored substance is just the basement membrane, and it doesn't impede the flow of these fluids. And then you see a fenestration, which is a nice big hole. You're going to see that in the fenestrations of the kidneys. All right, so what we call capillary exchange is that exchange of fluid and those things dissolved in that fluid leaking out of the blood at the arterial end, leaking back into the blood at the venous end. And so we have these opposing forces. The hydrostatic force is just the pressure of fluid pushing against the membrane. in the blood, the hydrostatic force is the blood pressure. But there's also a tissue fluid pressure. It may not be very big, but we have to account for it. So we have blood pressure in the vessels and interstitial fluid or tissue fluid surrounding the vessels, and the blood pressure is so much higher than the tissue fluid pressure that you have a gradient that allows this fluid to leak out of the blood vessels from the inside, where the blood pressure is high, to the outside. The opposite effect is the osmotic pressure. This is usually due to the colloid proteins, the albumin and the globulins predominantly in the plasma. So we call it a colloid osmotic pressure. And so you should always associate colloid osmotic pressure with the presence of proteins. Proteins are the colloids. And because there are so few proteins, if any, in interstitial fluid, there's a very low, like a 0 colloid osmotic pressure in typical tissue fluid. But of course we can disturb that with disease processes. The difference between the plasma and the interstitial fluid pressure is sometimes referred to as the oncotic pressure. All right, so this is a much better diagram because it gives you a better picture of what it's actually going to look like, and it also gives you the pressure. So at the arterial end on the left, we have a blood pressure of about 30. Look at the figure below the capillary. We have a blood pressure of about 30 out. We have a negative interstitial fluid pressure. So that's going to give us a total pressure of 33 out. The reason that interstitial hydrostatic pressure is negative is because the lymphatic capillaries are kind of sucking it out. So we have a net hydrostatic pressure at the arterial end of 33. At the venous end, our pressure has dropped drastically from about 30 to about 10, giving us a net hydrostatic pressure at the venous end of only 13. And then our osmotic pressure, because plasma has proteins and interstitial fluid doesn't really have that much. We have a difference of 28 and 8. That is our oncotic pressure. And I think 28 minus 8. 28. That 13 is wrong. So 28 in and 28 out. Look at the diagram above. It should be 20. So you have an osmotic pressure of 20 pushing in. So 20 pushing in versus 33 pushing out at the arterial end gives us a net outward pressure of 13, but 20 versus 13 at the venous end gets us a net pressure of 7 in at the venous end. So 13 out at the arterial end, 7 in at the venous end. 13 minus 7 is a net filtration pressure of 13 minus 7, or 8 millimeters of mercury pushing out. And since it's a net outward flow, that means more fluid leaks out than leaks back in, and that gives rise to that flow of fluid into the lymphatic capillaries. All right, here's just another diagram showing the same thing, hopefully this time without a math error. So slightly different values, but our normal range at the arterial end, 30 to 35 millimeters of mercury, osmotic pressure, 20 to 25. And we're just calculating the same values a little bit differently. So here we're seeing a net filtration pressure at the arterial end of 10 millimeters mercury out. At the venous end, negative 8, that means 8 pushing in, and 10 minus 8 gives us an overall of negative 2. Now, I'm going to go over these in class with you. I also have the practice problems posted for you, and we'll be going through those. All right, so here are our pressures. Hydrostatic pressure pushes against the capillary wall. Blood pressure pushes out. Interstitial fluid pressure pushes in, unless it's negative, and we'll talk some more about that. Osmotic, you should think of as a pulling pressure. Plasma proteins in the blood pull water in. Lack of plasma proteins in the interstitial fluid means it's not going to have much effect, but any proteins that are there are going to pull out. So here's a sample problem. If the blood pressure is 35 and the interstitial fluid hydrostatic pressure is 0, our net pressure is 35. Our blood colloid osmotic pressure, 26 minus 1, is a net of 25. So if I have a net of 35 pushing out and a net of 25 pulling in, then my overall net filtration pressure is 10 out, 10 in an outward direction. Okay, so that's what we see in this figure. Let's go to the venous end, where our blood pressure has dropped from 35 to 17. So with everything else being the same, now our colloid osmotic pressure is higher than our blood pressure. 25 minus 17 is a net of 8, and the direction has switched. So it's 8 pushing in or pulling in. And that's what we see in this half of the diagram. Okay, so here are some things we can change. What if the blood pressure is 45 instead of 35? All other things being equal, that's going to be a higher pressure pushing out of 10. That's going to double the amount of pressure pushing out. What if the colloid osmotic pressure is only 20 instead of 25? Well, that's less of a pulling effect. So I'm going to have less blood coming, or less fluid being sucked back in due to a low colloid osmotic pressure. So what would cause these? Well, your blood pressure can get elevated if you have too high of a blood volume, or if you have hypertension, or if you have congestive heart failure, and that excess fluid getting pushed out of the blood can cause edema, edematous tissue body-wide. And so what we see in people with congestive heart failure is that they're just puffy. Their ankles particularly are swollen. You see people walking around with their swollen feet jammed into these little tight high heels. They have systemic edema, and they have problems with hypertension. You're going to see colloid osmotic pressure drop too low if, for example, your liver is unable to make sufficient plasma proteins. Remember, the primary plasma protein is albumin, and that albumin is formed by the liver. So liver disease or inadequate protein in the diet, either one could cause a drop in colloid osmotic pressure. And in that case, you tend to see not systemic edema, but edematous tissue collecting in the peritoneal cavity, causing a big swollen belly. Okay, so here are the practice problems, and I think rather than going through these on the video, I'm going to go over them in class so that we have a chance to go through them. But here they are. The answers are all in that PDF online. So, and on your test, you will have 2 problems. I will always, when I ask you to solve the problems, I'll give you the numbers. So here you see in part 1, it gives you a sample situation, and in part 2, it gives you the numbers. I will, on the test, when I want you to calculate the problems, I'll give you those numbers, but I may ask you for any of these conditions in our sample problems, I'll ask you what, in what direction it would cause the fluid to flow. Okay, our last part, I think this is our last part, is on venous return. Remember that the blood flow in the veins is very low, and it can be so low that gravity can work against you. And there are some things that can happen, such as air embolism or syncope, which is just fainting, that can cause such a reduction in venous return that you actually don't have enough blood flow to the brain, and syncope is just fainting. So if your blood pressure is too low to the brain, you just pass out. That gets your head back down level with your heart, hopefully without hitting your head too hard, and reestablishes normal flow to the brain. We're going to see that skeletal muscles, particularly in your legs, create what we call a skeletal muscle pump, and even just breathing, as you suck air into your lungs, you're literally sucking blood into your heart. So if you're feeling faint, taking deep breaths can increase venous return. Contracting the muscles in your legs can squeeze that blood, assuming your valves are working correctly, can squeeze the blood back to the heart. So walking is good for circulation. And if you stand too long, then that blood just kind of quits flowing, and people do occasionally pass out just from standing too long, particularly military at attention in hot weather, or band members who pass out during a performance when they're standing too long. All right, I'm assigning you to learn circulatory shock. Here you see the causes listed. So make sure that you know what could cause each of those and what the mechanism is, and how in each of those cases the blood fails to flow, and circulatory shock then can be pretty quickly fatal. Circulatory routes, these kind of go along with the distribution of blood. Remember that in the brain there's very little fluctuation in flow or pressure. In the lungs, of course, we have a low blood pressure, and if the blood pressure gets too high, then you can push too much fluid out of the blood vessels and into the air spaces. That's pulmonary edema. And that's a pretty abrupt end, but we're done with the vessels.